Hello, and welcome back to our investigation of kinetics here in AP Chemistry. Today we're going to be covering topic 2, which is kind of an introduction to rate laws. So a couple of objectives today is being able to represent experimental data with a consistent rate law expression, and using the power of each reactant, all right, to determine the order of the reaction with respect to the concentration of that reactant. So previously, when we were talking about, or in our introduction to kinetics in topic 1, we learned that reaction rates depend not only on the concentration of reactants, but also the presence and the concentration of catalysts. And this is what we're going to be looking at today in terms of rate laws. Okay. So let's look at an example of a chemical reaction. Okay. Nitrogen dioxide reacts with diatomic fluorine, okay, to form something called nitrile fluoride. Okay. Now, without knowing this, all right, or if you went into the lab and performed this reaction, you would eventually discover that by doubling the concentration of both reactants, you would double the rate of reaction. Now, taking that information into account is very beneficial because that information, all right, which relates to the rate of reaction, okay, allows us to describe the rate law, okay? So the rate law relates the rate of reaction to the concentration of reactants and or catalysts to various powers. So if we look at that reaction again, okay, and take into account, what happens when you double the concentration, how that affects the rate, okay, this would be the rate law of this reaction. The rate of reaction is equal to K times the concentration of nitrogen dioxide to the first power times the concentration of diatomic fluorine also to the first power. Okay. So both reactants have an exponent of 1. Okay, it's kind of one of those things where you don't necessarily have to write the 1, but you can. The very presence of that indicates that it's at least a power of 1. Okay. Now, because we're relating a reaction rate to concentrations, there is this element of proportionality, and as a result, we have to include a rate constant, which we denote as the letter K. And it's also important to remember that this K is temperature dependent. If I ran this reaction at room temperature, okay, it would have a specific rate constant. If I ran the same reaction at 100 degrees Celsius, it would have a different rate constant. Okay, so it's temperature dependent. All right, now the general rate law is as follows. Here is a very basic chemical reaction. A plus B gives D plus E in the presence of a catalyst. Okay, where the capital letters represent the species, the lowercase letters represent the coefficients of the balanced equation. Okay, here is what a general rate law would look like. The rate is equal to K times the concentration of reactant A to the Q power times the concentration of B to the R power times the concentration of the catalyst to the S power. Okay. Notice what is not included in the rate law. What is not included? Okay. The products. Okay. The products are not part of the rate law, only the reactants. Okay. Also notice that the exponents or the powers are not directly correlated to the coefficients of the balanced equation. Okay. Later on, when we start learning how to calculate or determine these values, some cases they match up to the balanced equation, sometimes they don't. Okay. So these letters, the Q and the R and the S, have to be determined experimentally. Okay. So the powers or the exponents are determined by experimental data. Okay, which we'll get into later on in this unit. Okay, right now we're just kind of doing an intro to how to write a rate law and what all the variables represent. Okay. Now, why do we care about the rate law? Okay, previously we learned about the reaction rate. We thought that was good enough. Okay, but that is not the case. Okay, because what the rate law does is that it includes all of the reactants to determine the reaction rate. Okay. The reason why we care about this is that you can calculate the rate of reaction for any value of the concentrations of reactants. So for example, if you knew the rate law and you're like, I need this to run for 2 hours, what's the best efficient way to do this? You could calculate the amount of concentration, or the concentration of reactants that you would need to determine when the end time of that reaction would be. Okay, so it's a great way to maximize the efficiency of a reaction. Okay? In fact, my wife, she spent the first 3 years in graduate school determining rate laws for some methodology reactions that she was doing in her research group. Okay, so it's a very powerful thing to know for a reaction. Okay? Big pharmaceutical companies save a lot of money knowing the rate law of a particular reaction. Okay, so another important aspect of a rate law is something called the reaction order. And this is specific to the exponent for the reactants in the rate law. Okay? So if we go back to our example, okay, the synthesis of nitrofluoride, here was our rate law. Okay, the rate is equal to K times the concentration of NO2 to the first power times the concentration of diatomic fluorine to the first power as well. Okay, the exponents gives us the reaction order. Okay, so if it's an exponent of 1, it is first order nitrogen dioxide and first order diatomic fluorine. Okay, and again, the exponents do not always match up to the coefficients of the balanced equation. Okay, so your instinct might be, oh, this is second order, but it's not. It's first order. Okay, and the order is basically telling us how the concentration of that reactant affects the rate law. Okay, so as imagine if this was a 2 or a 3, or as the numbers get higher, those reactants have a greater influence on the rate of reaction. So if there is a order for individual reactants, there's also an overall order to the chemical reaction, and that's basically the sum of the reactant orders. So in this case, this is first order NO2 and first order F2. We take the sum of those. The overall order for this reaction is second order. Let's look at this equation. Okay, this is basically a isomerization of cyclopropane to propene. Okay, now, can you predict the rate law for this reaction? If so, provide it. Okay. You actually couldn't, okay, because you need experimental data to come up with this reaction, or this rate law. So the rate is equal to K times the concentration of cyclopropane. If I ask you what the first order is, you would say first order CH3H6, first order overall, only because there is one reactant, and that reactant is first order. Okay. All right. Here's another one. Here's another example. Okay. Here's the rate law for this reaction. Again, we cannot determine the rate law without experimental data. So I took the experimental data and I wrote this up. Okay. Later on in this unit, we're going to figure out methods on how to determine these. Okay. So, what is the reaction order of nitrous oxide? What is the reaction order for diatomic hydrogen? What is the overall order? Second order NO, first order H2, third order overall. And that's it, folks. That is topic 2, rate law. Hopefully, I was able to show you how experimental data can be written to represent a chemical reaction in the form of a rate law, which is very powerful because we can use that to maximize the efficiency of a chemical reaction. Okay? And then finally, the power of each reaction is the order of the reaction with respect to the concentration of that reactant. All right, thank you for your attention today. Have a great Thanksgiving break.